Pre-calc, Chapter 2, Section 2. So we're going to look at polynomials here, and we're going to look at transformations in behavior, zeros. Polynomial function. A polynomial function has a graph that is continuous and smooth. So that's what we sometimes call it a curve. So we look at this continuous and smooth curve. This is x cubed. We should be familiar with that. That's an example of a polynomial function. The leading coefficient test, given this polynomial, so we can expand the polynomial like this, which really we're looking at the leading coefficient and then the degree of it. Those are the two things we're going to look at when we look at polynomials. If n, the degree is even or odd, that's the first thing we look for, because that tells us the parent function or the shape. So if we look at evens, like so x squared or x to the fourth or x to the sixth and so forth, x squared is a parabola, and it could open up or down. X to the fourth could be a parabola, but if you start adding these other terms to it, it could end up being the W shape, and so it has these humps on them, the turning points, and so x to the sixth, it could just have more of these humps. Now notice how the arrows here, the arrows both go in the same direction. If you zoom out, this would actually end up looking like a parabola to some degree. And so the overall shape is kind of like the parabola. And so the turning points here, if you look at the turning points for x to the fourth here, we have 1, 2, 3 turning points, which are like relative max or mins, which we can find those. This one we would have 1, 2, 3, 4, 5. So you should see a resemblance in the degree and the number of turning points. This only has one turning point, so the degree is 2. That's the most amount of turning points a polynomial could have. It doesn't have to have that. X to the fourth could just be a basic parabola as well. If it's an odd function, so if we look at odd, we have x to the, we can start with x to the third, x to the fifth, x to the seventh, and so forth. These have this shape to it, cubic shape to it. X to the fifth could just have more humps in it. And the most amount of humps x to the seventh could have would be one less humps, would be 6 humps for that one. Kind of like Fergie, more humps, more humps. So we have 1, 2 humps for the degree 3. We'd have up to 4 humps for degree 5. The turning points up to 6 turning points for degree 7. These, notice how they're in behavior, the arrows, they're going opposite directions. We still think left to right at this graph. Left to right, this graph is going upward, so that'd be like a positive. Arrows go opposite directions here. Now that's the even odd degree, tells us the shape of the function. Whether the leading coefficient is greater than 0 positive or less than 0 negative, that describes if the function is increasing, going upward, or decreasing, going downward. These are called end behaviors. And what we're saying here is as x goes to positive infinity, what direction will the y values go? So if n is even, like these red ones up here, x squared, x fourth, x to 6, and a is greater than 0, so they're going to be going upward, our y values are going up, so it's to positive infinity. As we go to negative infinity, as x goes to negative infinity, which means left, then the y values still go up because our arrows are going the same direction. Now if we flip that and have our a value less than 0, now these are going to be both going downward. So as we go to the positive infinity, which means right, the y values go to negative infinity. As the x goes to negative infinity, which means left, the y values still go to negative infinity. For the n is odd, the purple graphs here, if a is greater than 0, if we go right, which means if x goes to positive infinity, the graph goes up, so y goes to positive infinity. As x goes left, y would go down. And then if a is less than 0, we reflect that, so we're going downward. So as x goes right or positive infinity, the graph would go down. As x goes left, we would go up. So these behaviors are always true, so you don't necessarily have to graph it. If you kind of look at the first term here and just know the leading coefficient sign and whether the degree is even or odd. So let's just make up 2 examples here. So we have these two. We can look at just, all we need is the degree and the leading coefficient here, which is 1. And all we care about is that the degree is odd and that the leading coefficient is positive. We don't really care what the number is. We care about degrees odd or even, leading coefficient is positive, negative. So I now know that because it's odd, the arrows are going opposite directions, and the leading coefficient is positive, we're going upward. So as x goes to positive infinity, which means right, the f of x, or the y values, are going to be going up. As x goes to negative infinity, then f of x is going to be going down. And if you need to sketch it out, you can. This is going to be the sketch of that. So as we go right, the graph goes up. As we go left, the graph would go down. And that's kind of the end behavior. We're looking really far off to the side what's happening. The other one, as x goes to positive infinity, I know f of x for this one is going to be going to negative infinity. And as x goes to negative infinity, the y value still goes to negative infinity. And I know that because the even degree means the arrows go the same direction. The negative means we're going downwards. It's going to have this shape to it. Two quick examples. Zeros. Zeros is when we take the equation, whatever the y is equal to, and set it equal to 0. We want to know when, at what x values do we have a y value that's equal to 0. So we're finding zeros, we're going to find what the x values are that make the y 0. So the function f has at most n real zeros, and we're still using the polynomial notation, like the ax to the n plus ax to the n minus 1. So we could call this the nth coefficient, the n minus 1 coefficient, and so forth. So the n that I'm talking about here is the degree of the polynomial. That's the degree of the polynomial, is the n I'm talking about right here. So the number of zeros we can have is at most the degree of the polynomial. So the graph has at most n minus 1 relative extrema, or maximum ends, and those are the turning points we talked about, one less than the degree. The real zeros, given a is real. The x equals a is a 0 of f. X equals a is a solution for f of x equals 0. X minus a is a factor of f of x. And a0 is an x-intercept. So a is just the actual 0. If you found that 0, these are different ways to represent the 0 or solution, factor, x-intercept. These words, 0, solution, factor, x-intercept, and there's one more word, root. Those 5 words are all talking about the same point. Now they can represent that multiple ways, as like x equals your solution. You can write it as a factor, or you can write it as a point, an intercept. And so different ways to represent that solution, but they all are talking about the same spot. A repeated 0 with multiplicity k occurs with factor of x minus a when k is greater than 1. All we're saying here is that sometimes you have more than one factor. So if I had like x minus 2 to the third power, that has multiplicity to it. It has a repeated factor. So that 0 of x equals 2 occurs more than once. So this one would only occur once. This one here would occur 2 times. And so if k, if the degree on that is odd, the graph crosses the x-axis. If k is even, the graph touches the x-axis at that answer, which is a relative extreme. So for the example down here, where I have my solutions, I set each of these quantities equal to 0. I find x is 2, x is 1, and x is negative 5. I know that this one's really a special one because the even degree tells me that this is a double root, which means that this is going to be a turning point. It's going to be a relative max or min when I graph that. The odd ones just means it crosses at that x-intercept. So here's some examples. Let's find all the zeros for these. So finding zeros, we really need to use our factoring skills or our quadratic knowledge. So here I see both these terms have an x squared. They also have a 10. I can factor out. I'm actually going to factor out a negative 10x squared. If I factor that out, I'm left with x squared minus 1. And then this factors again to x minus 1 and x plus 1. After we have it factored, we set each factor equal to 0 to find all of these zeros or solutions. And so we have x would equal 0, 1, and negative 1 are the three solutions. We should have a fourth one. Now what's the fourth solution? Again, this one is x squared, so it really has two solutions. So this 0 is a double root. It occurs twice. You don't have to list it twice, but you can realize that the fourth solution is 0 again. So here we can look at, again, they all have an x, so let's factor out an x, and I'm left with x squared minus 12x plus 36. And then we can go through and factor x, minus, and 6, and 6. So these multiply to be 36, and they have an OI value that is negative 12. Now that's the factor form. Now we have to find the solutions from that. So again, set each factor equal to 0. So I find that x is 0, 6, and then 6 again. So I could just say 0 and 6, realizing that 6 again is a double 0. So we have list the zeros in graphs. So in the factored form, we could first find the zeros. So this 0 here would be 1/2. This 0 is negative 3. This 0 is 4. And you find that again by setting each of the parentheses, the quantities, equal to 0. That occurs because the whole thing has to equal 0. And the only way for products to equal 0 is if one of these products is 0. So we can then plot these. So we have 1/2, negative 3, and x equals 4. Those are 3 points. Now realize the degree of this polynomial. It's squared, cubed, and to the first. So if I add those up, this is really like an x to the 6th power. If I want to figure out what the leading coefficient is, I'm doing 2 times 1 times 1. So this is going to make 2x to the 6th plus, this is the first term. So I know it's going to have an x to the 6th shape, which is going to have, it could, some kind of W, it could have more humps than that. The arrows are running upwards. So I know from that shape, I got to kind of make that shape by these points. Now, the other thing I need to pull out here is that this is a double root 2, which means at that 0, 1/2, we are not crossing the x-axis. We're hitting this and turning around. That's all we're doing. So, and it's actually going to go the other way. We're going to hit this and turn around. And so I know when I'm graphing this, I'm going to come down through this point. At somewhere down here, I'm not quite sure, I'm going to come back up, hit this turning point, come back down, and then back up over here. So I can sketch the graph. When I'm sketching this, I'm not really trying to do create a lot of points. I'm looking for these 3 points, the shape, and seeing that this is a turning point. So that's all I'm really looking for or assessing. Last example is write the equation if the zeros are. So if I tell you these zeros, and I tell you that this last one has a multiplicity 2, so 3 with a multiplicity 2. So we can take these zeros, so x equals negative 1/2, and I can change that into factor form. So if I add it, it's like x plus 1/2 equals 0. If I multiply both sides by 2, I get 2x plus 1 equals 0. So I can write it like that instead on the fraction. So that's, you can write this as the factor. So if I write out the factors, this is 2x plus 1, that's from the negative 1/2. Negative 3 comes from x plus 3, and then 3 comes from x minus 3. But because this is multiplicity 2, I have it squared. So this would be the equation in factor form. So for your homework problem, this is your video problem that I want you to turn in for tomorrow. I want you to take this function here, and I'll just call it that. I want you to take this function, I want you to try sketching it on a graph. And so you just sketch it, and I'll look at the visual graph to see if you can find it. So that is going to be it. Have a good night. See you tomorrow.